Black holes are supposed to trap everything, even light, so how can they lose anything at all? That's where Hawking radiation comes in, you see. In 1974, Stephen Hawking did something radical. He applied quantum mechanics to the edge of a black hole. What he found changed physics forever, really. At the event horizon, the invisible boundary around a black hole, quantum theory says particles constantly pop in and out of existence. These are called virtual particle pairs. Normally, they cancel each other out almost instantly, but near a black hole, one might fall in and the other escapes. To an outside observer, it looks like the black hole just emitted a real particle. That's Hawking radiation. Here's the twist. Energy can't just appear out of nowhere. So when a black hole emits this radiation, it loses a tiny bit of its own mass. Over time, it gets smaller. And if it keeps radiating long enough, the black hole could eventually vanish. This was the first time anyone showed black holes could evaporate. It linked quantum theory, gravity, and thermodynamics, three areas that usually don't get along. And it raised huge questions. If black holes can disappear, what happens to the information that fell in? That's the information paradox, another Hawking mind-bender. You know, we've never directly observed Hawking radiation, it's just too faint to detect with today's tools. But hey, the theory holds up mathematically. So if Hawking was right, black holes aren't forever. They slowly glow, fade, and eventually they just disappear. It's kind of like discovering that the universe's darkest objects are quietly leaking light. Mind blown? Well, hit like, subscribe, and drop a comment. Do you think we'll ever detect Hawking radiation for real? Stay curious, and keep Debunkify.